Okay, this is going to be lecture number 5. In the previous lecture, we had gone through the various octave band, 1/3 octave band filters, how it is designed to mimic the human ear characteristic, and we also talked about weighting scales, the A weighting filter, as well as what Per Bruel has suggested that we should use a D scale. I showed you some of these in the previous lecture. So you can see the A scale, which is the blue line, and the D scale, which is what Per Bruel is advocating. So this B scale is highly accurate below 1 kilohertz. Unfortunately, this has been discontinued from the standard. We stick with a slightly erroneous scale, which is sometimes, that is why I often remark that standards need not be a holy grail. All right, so let's go back. Let's see what we have. So we talked about the Z scale being the old linear or unweighted scale, so which is basically flat response from 10 hertz to 20 kilohertz. And we said, okay, the next thing that we wanted to know is, okay, we are measuring the sound levels in each of these noise spectra. The question is, how do I add these up? I'm going to quickly show you. We will use the clapping example in order to put together the data together and then be able to look at the overall sound produced by my clapping. Okay. In this, of course, I have assumed, even though I have recorded this, it is in voltage. I have simply, for the sake of computing, I assume that there is a 1-to-1 correlation between, that means the microphone that I have used essentially is 1 volt per Pascal, so each volt is basically treated as a Pascal. May not be the case, but just for the sake of computing, I have done that. So let's go back, look at, let me play back, before I do that, let me play here the whistling, for example. Just recall, this will play the whistle. Hopefully you'll be able to hear that. So this was the whistle which we showed. I will show you the spectra for this, and this is the time for which I have captured my clapping, which is definitely irritating. Okay, so we recorded those, as I said, I will show you the spectral characteristics that I have got from running it in octave. So here is the spectrum for the first one is the whistle, which is very focused. In the video, I think the second video, if I am not mistaken, second or maybe the third video, I told you to trust me that the frequency content of my whistle is around 2 kilohertz, and this is what you can see. So you can see that when I whistle, there is very little. Of course, there's some 2 times the harmonic and 3 times the harmonic, but the main sound of my whistle, the energy is focused around 2 kilohertz. So that you can see here. This is voltage, but as I said, I am going to think of that as sound pressure itself for my calculation, just to show you some levels. This is the clapping spectrum. So you can see, unlike here where it is very focused, sharp around 2 kilohertz, here you can see it's fairly broadband, which is what most impulsive sounds are. They do have energy content over a large range. You can see that I have this right from 0 around low frequencies 2 kilohertz, and then maybe a little to about 3000. So there's a range from about 500 to 3000, and then it or 2000 hertz band, and then it drops off after that. So that's the content for clapping versus whistling. So what we are going to do is, I am going to convert this into basically the data for clapping, which is what I have converted. You can see now I have converted this. Now how do I convert this? I have written a small code. I will share that. So basically we are looking at applying the bandpass filter to this. So imagine now I have this FFT, so I am going to look at adding things only within that particular band, right? So if I take, for example, my 1000 hertz band, the bandwidth basically goes from 1000 by the square root of 2. It's an octave band, which is what it is. You can see there at the screen. So 1000 by root 2 and 1000 times root 2, so it roughly goes from 707 to 1414. So a span of 700 hertz. So whatever FFT that I took and the spectra that I took, if the energy that falls within that, I'm going to square and add and the pressures and then get a value. So you can clearly see that the whistle, which is the red, dark red solid thing, you can see is very dominant at 2000. Not surprising, because most of the energy you saw was around 2000. And it drops off very quickly on either side of it. On the other hand, clapping, you can see has at least it doesn't drop off first of all as sharply as the whistle, and you can see that even at 250, 500, 1000, 2000, 4000, 8000, it is not insignificant compared to the dominant one, although it is about 10 dB difference or whatever. Alright, okay, so that is fundamentally the thing to this is bandwise data. So I'm going to now only look at I'm going to basically look at bandwise levels at this. You can see whatever I showed as a set of bars. I have now documented the values. 62.5 is 63. 32.7 dB, 48.5, and then reasonable numbers once you come to 250, 500, 1000. So you can see the dominant numbers are in the 1000 and 2000. So 77.6 and about 82.1, and about 70 dB at 4000, 8000. So you can see there are 3 or 4 bands which are basically strong, and if we do the A weighting, if I apply the A weighting, so you can see that 63, the A weighting is almost 26 dB, so it drops down to about 6.5, which is virtually nothing. And as you can see again, at 1000, of course, it remains at 77, and around 2000 there is a small addition in 2000 and 4000 hertz band. There are small additions. And once we go to 8000, again there is a small subtraction. Now I've added all of this and then come up with a number which is, see, often you are interested, okay, band wise we saw the energy, so looking at those bands it's very clear where the sound is, what is the dominant sound. So by looking at this, if someone hands you this kind of a plot, you can see, okay, you don't know that it is clapping or you don't know if it is whistling, but you can clearly see where the sound or what spectral components are present in the sound, right? So we said 2 things that matter as far as sound characterization is concerned: understanding the frequency characteristics. So these are spectral characteristics. The second, that each of those frequency characteristics associated amplitudes. So the job is to understand what contributes to that frequency characteristic, and of course how do I reduce the amplitude in the case of a machine, right? While we are doing the design. Obviously you can say just stop whistling. Obviously that's the best noise control you can do, and of course if you tie my hands together so that I cannot clap, but that's we are not dealing with humans here. I am going to generally deal with the machines. Alright, so let's see how do we do this. It's a simple process by which we do this. So here we have given sound levels for each 8 bands. So what we do is we actually add the mean square pressures from each band. So the energy in each band is represented as P band square is P reference square. So you remember the sound pressure level is 20 log base 10 P RMS by P reference, which can also be written as 10 log base 10 P RMS square by P reference square. And the P RMS square is the mean square value. So we can, if you divide the LP by 10 and take the power of this, we get the energy that is present in the band. Now we sum up all of these. So I have different bands. If I sum it up, I get the overall energy level that is present in the entire signal. So we can convert this, we add up all of this and then basically now do a 10 log base 10 P reference square, and then it turns out we have a LP total which we can compute. So if you look at the previous slide, The LP, which was the Z weighted, if you want to call that, is 83.8. But when I do the A weighted summation, so all of these are summed in the same fashion. I go, all of these bands I can add, all of these bands I can add. I can write a small spreadsheet or a small Octave program and I can add that. So you can see there's about a 1 dB difference, 84 dB, roughly 83.8, goes to 84.8 in the A weighted level. This is an interesting scenario where the A weighted scale is actually higher than the Z scale. Normally that doesn't happen. The reason that it happened in this case is because the dominant energy is in the 1000 and 2000 hertz band, where the human ear is very sensitive. Now, of course, one can write an Octave or a spreadsheet and then do this through a very systematic fashion. But I can, I as an engineer, I will like to look at this data and then say quickly arrive at some numbers. So I'll tell you how to do this. So these are called shortcut calculations. So for the shortcut, what I'm going to do is we look at the various bands and see what is the difference between the various bands. For example, let's say the 500 Hertz and 1000 Hertz are each 82 dB. Now when I add two bands which are exactly the same value or near about the same value, the combined value is 3 dB more. So if I have 500 Hertz, the LP was in that band 82 dB, 1000 Hertz also was 82 dB. Then when I add them together, I get 85. Right? Now, what if I want to add an 82 and an 81? If the delta is 1 dB, then the 82, 81, when I add, I will get 82 plus 2.5, which is 84.5. Similarly, if it is 2 dB, 82 and 80 added together will give me 84. So you can see that for 2 or 3 dB difference, if I add, I get about 2 dB. I have rounded it off. You can see that I have rounded it off to half dB levels. I have not been very picky about saying that it should be 1.89 or whatever. Round it to the nearest thing so that you can get a quick estimate. So obviously this quick estimate may not be exactly what you get by your systematic calculation, but it quickly tells you what the ballpark noise level is going to be. Okay, so up to about 6 dB you can see that 1 dB is about 2.5, 2 or 3 dB difference is about 2 dB. 4 is about 1.5, 5, 6, 7 is almost like a half, 5 and 6 is effectively 1 dB difference. Now if the difference is 8 dB or more, so if I had 82 and 74, the mathematics simply says 82 plus 74 is 82. Okay, remember this is log scale, this is not when we say 82 and 74 are being added, the dB levels are being added, therefore you can see that one can simply say the sum is the higher of the two SPLs. So anything more than 10. So let's go back and apply this to logic to this. So let's come back and look at this. So let's see. Between 32 and 48, there's virtually no, 16 dB difference. So effectively, if I add 32 and 33, if I want to call that, and 48, I will get effectively 48.5. Now, when I add these two, 62.3 and 67.2, there's about a 5 dB difference, and the sum of these is going to be 68. Right, 68.2 if you want to be more precise about this. 5 dB difference, we said 1 dB is the gap. Right, 5 and 6 was 1. Now, so if I add 48.5 and 68, obviously again nothing is going to change. So that's so if you look at 1, 2, 3, 4, the first 4 bands, effectively added up is 68, and that 68 is because 250 and 500 are 5 dB apart, so it will be 67 plus 1 dB, so it's about 68. Now we'll let's before we do the 1000 and 2000, let's come down and look at the 4000 and 8000. They are within about a dB of each other, 68.8 and 69.7, so 1 dB difference. Our shortcut method said that if they are 1 dB difference, the effective addition is 2.5 dB. So if I add 69.7, which is roughly 70, I get 72.3 is what I get from adding the 4000, 8000. So now you see the first 4 bands is at around 68. The bottom 2 bands are at around 72. Now let's look at 68. If I compare with 72, this is 72.3 and that is about 68.3, right? Roughly about the same. So 5 dB difference. So again, when I add these two sets, so the 6 bands together will be about 73.6. Now let's look at 73.6. Now marries with the 77.6, 4 dB difference. We said it's 1.5. So therefore that's 79.2. Now 79.2 and 82.1 is roughly 3 dB, which is again basically going to be about 2. So roughly the overall sound level is 84 dB. So this is the quick dirty calculation. So we can do the same for the A-weighted scale. I will leave you to do that. So that's what I've done with the shortcut. So you can see that whatever I have explained in the video, here you have a slide. We say we ignore the first two bands because they are very well below the other bands, so they won't create anything. So the beauty of it is, even though there is some noise in those bands, they don't make any impact on what you hear finally. So adding 62 and 67, we saw that you got 68. Adding the bottom two, we got 72. If you add these two, I got 73.8 because that's a 4 dB difference. And combining 73.8 with 77.6 gives us 79. And so finally 82 and 79 you add, you get about 84 dB. The exact value is 83.8, right? So, but this is a quick and easy way to sum up band levels and get an overall estimate quite quickly in your mind. So you can tell your boss, for this whistling it is, or clapping, I think we have done this with clapping. Clapping is about 84 dB. Alright, you can do a similar exercise. I leave it to you to do that for dB levels, and then you can come back and report that, check it out what the value should be, and I can confirm that. Alright, okay, so we have seen various things. Now we go into two more things before we look at the issues of sound pressure measurement, and then how we can fix that sound pressure measurement. So before that, we look at earlier we looked at traffic noise, community noise, and so on. We will now look at what is called as room design. So when you look at these things, we worry about, so far all of these were very objective measures, right? So you said there is a frequency associated with it, there is an amplitude associated with this. These are objective measurements, and therefore it's easy to understand. But as a human being, we also have a perception which is more qualitative, right? We have seen earlier that your hearing sensitivity varies with frequency. We tend to attenuate low frequency sounds and amplify in a certain band around 1000 hertz, and then again it attenuates further below. But when somebody asks, is it loud, is it not loud, a lot of these things are more qualitative, right? So therefore, we define this subjective term in terms of a quantity called phone. So what we call as equal loudness contours. Now what do we mean by that? So when we play 100 hertz sound, theoretically, let's say if it is if the level is going to be 80 dB, now your perception, we have seen earlier, it will be like 60 dB. So therefore I have to play a 100 dB sound in order to make you believe that it is 80 dB, and at 1000 I have to play it at 80 dB. So this loudness contour phone is basically kind of an inverted curve of this A-weighting filter. It is the unit for loudness. We use 1000 hertz as a reference because that almost all humans are equally sensitive at 1000 hertz. Now when we say this phone definition, so here is a curve just to show you. So this will be kind of like an inverted, if you look at the curve, it's kind of like an inverted A-weighting curve, right? So each of these lines is basically a contour corresponding to, so for example here is an 80 phone curve. So you can see that the curve, I have to increase the sound level at low frequencies in order to make it appear equally loud. So as it comes down as you go to higher frequencies. A little bit from here you can see it starts to become more sensitive, and then again the sensitivity drops, right? So and then again you can see some I have to so here is the most sensitive zone where I have to reduce the sound level in order to hear it the same way, and then again as I go to higher frequencies it picks up once more. So the sound is perceived as equally loud to 60 dB at 1000 Hertz. What sound level I need to have? So a 60 phone sound, when I say the loudness is 60 phones, we look at what amplitude I need to give to the sound at a particular frequency to make it appear as loud as what it was 60 dB at 1000 Hertz. So this is one of the ways that you can now we say equal loudness. So if you look at that curve, so let's say 60 dB at 1000 Hertz. Let's go back to that curve. So 60 dB at 1000 Hertz, so which is what we are here. This is this line. So the line here, that is what we are following. So now if I want to have 100 Hertz, if it has to appear equally loud, you can see that I have to nearly have about 70 dB. So close to about 70 dB sound will sound equally loud at 100 Hertz as it will do. A 60 dB sound will appear at 1000 Hertz. Now obviously if I go down to, let's see, here we have I think this is 4000, no 5000 maybe, no I think that's 4000. At 4000 Hertz if I go down, then effectively something which is what we'll see, what does that sorry, I was in the wrong curve, I was looking at the 70 dB curve. So here is the 60 dB curve. So when I go to 100 Hertz, so this is the curve that I should sit in. So when I go to 100 Hertz, it's about 70 dB, that is right. And when I come down to about 4000 Hertz, I really come down to almost 50 dB. So a 50 dB sound at 4000 Hertz will sound as loud as a 60 dB sound at 1000 Hertz. So because your ear is more sensitive, even a lower sound appears to be loud. Alright, so this is one way of measuring this. And then we have another scale which is basically going to be a rule of thumb for loudness, right? So this is called a phone. So phone is 1 unit of loudness, which is a measure of subjective measure, and the other unit is basically a phone. It is related to the phone. So and this is a very subjective metric. So what happens is that when people are asked to listen to these sounds and then come up with kind of a thumb rule. So if the pressure amplitude increases by an order of magnitude, so 10 times, and then people say, okay, it appears as though it is twice as loud, right? So this is of course completely based on subjective measurements, but that is important because when you're doing noise control, this kind of information is very, very useful because we will see shortly that unless there is a certain amount of sound reduction, people will not perceive that there has been a change in the loudness levels. Okay, so if an amplitude increases 10 times, it is perceived twice as loud. So therefore we have this zone, which is defined as log base 10 of S, which is the zone value, is 3 by 100 into P minus 40. So obviously one zone. So if I look at P equal to 40, that is the loudness value, phone value is 40. So you can see 40 by, this will be log S will be 0, which means S will be basically 1. So one zone corresponds to a 40 zone. So you can see if P goes from 40 to 50, right? So that is about 30 by 100, 0.3, which is 2. So when I go from one zone to two zone, the P has changed by 10. So which is a 10 dB increase, right? Alright, so that is another thing. So what does this mean? So just quickly to give you, so even though in reality, see 3 dB change is actually, if you look at the amplitude has dropped by half. So if I reduce by 3 dB, so let's say I go from 82 to 79. So you go back, work the calculation, you see that my pressure amplitude has come down by 0.5. So it's a significant change. You will think, I have brought it to 50%. But interestingly, if you ask someone, they say, okay, yeah, I think there's a small change, but maybe a little bit, but not so great, right? So it takes about 5 dB for somebody, difference in sound levels for somebody to say that yes, there is a distinctly perceptible change in sound levels. So if you are a noise control engineer, you cannot say I made small tweaks in the design and I got a 2 dB change in the overall value. 2 dB may look nice, but unfortunately when you test it out, somebody is going to say, I don't think anything has changed. Alright, so 5 dB is the minimum target that you can have. 10 dB will be where people will say, well, it sounds half as loud as what it was before. And if you can achieve 20 dB, which is very, very difficult, they will say, okay, you have actually 20 dB, of course, increase would mean extremely loud, but 20 dB means it is much, much quieter than what it was before. Okay, so all of these are based on the zone definition is based on a number of experiments. So this 3 by 100 into p minus 40 and all that came from carrying out detailed experiments, subjective experiments with humans. Now, so the key takeaway from all of this is that, as I said, the sound reduction of a product has to be minimum 5 dB to make a perceptible difference. Anything less than 3 dB will not be perceived to have made a difference. So very important thing that you have to keep in mind when you're doing this. Alright. Now, one last thing before we close for this particular recording. We talked about subjectivity, then we also want to have single ratings to kind of look at how good your room is. If I want to have an office, what should be the kind of noise rating so that it is comfortable for people to sit and work with. So we will look at what is called as noise criteria curves, NC. Which is primarily to rate indoor noise, so that means working spaces, housing, etc. inside, as opposed to community noise, which is the sound coming from traffic and other things which we saw a little bit earlier. So this is inside the room, which of course could be because of traffic noise or whatever that is flowing in. We used to rate this as there are two things. One is the noise criteria curves, which is primarily used in the US. The Europe uses something similar called noise rating curves. So what you do is you actually sit and do a sound level measurement in the room, and the bands that you go from is 63 to 8000. You saw that in my addition, right? So you saw me adding those kind of things. So here's these are the NC curves. So NC 15 effectively means that I am right around, you can see that the numbers are within about 2 dB of the rating that you have at 1000. So NC 15 corresponds to 17 dB at 1000. And of course you can tolerate almost 47 dB at 63. They're okay. So an NC 15 curve would be something like this with these recommended values and so on, right? So you qualify and say my room is basically has a rating of NC 45. That means that this is the curve, your measurements come closest to this particular curve. Alright. So values define the limits of octave band spectra that must not be exceeded. Right. So to meet occupant acceptance in, so an example I will show you. So this is a room which has a NC 45 rating. So you can see that the measurement, obviously these are the NC curves, and the measurement obviously doesn't quite fit any of these curves. It has its own trend based on the kind of noise sources that are there. So what we do is the NC 45 or whatever rating that we are coming up with is basically based on the lowest curve that is not touched by the spectrum. Okay, so this spectrum you can see intersects everywhere. The NC 40 is here. The lowest is of course NC 15. So we are going upwards like this. Although it seems like it is touching there, it does not touch. The value is a little lower. So all of these are below the one curve which does not intersect. The first curve that does not intersect. The NC 40 intersects here, NC 35 intersects here, and so on. So the NC 45 is the first curve that is not touched. Therefore, this room will be rated as NC 45. So that is the NC 45. Now obviously you have to have what does NC, just saying that it is NC 35 or NC 25 or NC 45 has no meaning. So people have ratings. So they give you typically, these of course is based on a lot of test data. what is the recommended sound level, and there is an equivalent, the recommended NC ratings, and what is the corresponding somewhat sound levels, right? So you can see an apartment, so which means a living space. You would desire the NC rating to be between 25 and 35. Now, if you are looking at a stadium, of course not when a match is going on, because that is probably going to exceed substantially over here. Sports stadium is 45 to, so when we say NC 45, that's probably a good thing for a stadium. Now, in a factory, obviously we are allowing anywhere between 40 to 65 depending on what kind of factory it is. You see that, so most of these things, a restaurant 40 to 45 because it's slightly different ambient, but you see a TV broadcast studio, it says studies, it should be a studio, it should be 15 to 25. So obviously I expect the NC rating to be a lot stringent, so the DB levels to be a lot quieter. So depending on the kind of inner space, so whether it is a residential, part of a residential house, you are doing a recording studio, movie theater, whatever it is, you pick the appropriate, you have to qualify it to the appropriate NC curve. That's basically the idea. I think I will stop here with this session. We will look at the equivalent European NR curve. So it is very similar idea to the NC rating. We will come back and see that. And then one last thing that we will see is, all of these you have seen are based on sound pressure measurements using a sound level meter. There are some issues with this. We will point out what those issues are and how do I overcome that with a different metric. All right. Okay, I will stop here.